Hey guys, so in this video we're going to be taking a look at this thing called the complex number plane. Now a plane is simply a 2D map with two coordinate axes. So for example, I'm sure you've heard of the Cartesian plane, or it's also known as the XY plane, which looks something like this. So this is called a plane because it has two coordinate axes, an x-axis and a y-axis. And we can access any point in this plane using a pair of numbers. So for example, I could find the point that is 4 across and 1 up. And so this point would correspond to the pair of numbers 4, 1. The complex plane also has two axes, but instead of the x-axis, we have the real axis. And instead of the y-axis, we have the imaginary axis. Now on the real axis, we have all of our real numbers, like 1, 2, 3, 4, -1, -2, etc. And on the imaginary axis, we have all of our imaginary numbers, like I, 2i, 3i, 4i, -i, -2i, and so on. So how it works is if you have any complex number, say 3 plus 2i, then we can plot this number in our complex plane. Now the real part of 3 plus 2i is 3, so we go across 3 units on our real axis, and the imaginary part of 3 plus 2i is 2, so we go up 2 units on our imaginary axis. Then we find the point which corresponds to these two markings, which is here, and this point, which we'll call P, represents the complex number 3 plus 2i. In general, if we take any complex number a plus bi, then to plot it in our plane, we go across a units and we go up b units. And the corresponding point represents the number a plus bi in our plane. Now it gets annoying to have to write I, 2i, 3i, and so on every time we label our imaginary axis. So to make things neater, we usually just leave out the I and write 1, 2, 3, 4, etc., like we did with our real axis. So just remember that the imaginary axis is always the imaginary part of our complex number, while the real axis is always the real part. Let's do a couple more examples to make sure we understand the complex plane. So say we want to plot the complex number -3 plus I. Well, the real part of -3 plus I is -3, so we'd go across 3 units to the left, like so. Now the imaginary part of -3 plus I is 1, so we'd go up 1 unit along our imaginary axis, like this. And this point now represents the complex number -3 plus I. Last one, let's plot on the same plane the complex number pi minus 2i. And just to avoid confusion, I'm going to call this point Q instead of P, because we already used P for our complex number -3 plus I. So to plot our complex number pi minus 2i, we go across to the right pi units, which is about here, and then we go 2 units down to -2, like so. Great, so now we should be good with plotting pretty much any complex number. Now the next thing we're going to look at is quite tricky, so brace yourself. Let's go back to our complex plane and plot the number a plus bi, like so. Now plotting a complex number by going across a units and up or down b units is great, but that's not the only way to do it. If we were to draw a line from the origin of our complex plane to the number itself, like so, then we'd see that you could find any complex number just by knowing the length of this line, which we'll call lambda, and the angle that it makes with the real axis, which we'll call theta. Theoretically, we could do this since any complex number will always have its own angle and distance from the origin. You can think of it like a game of battleships. If you can point your cannon in any direction, and you can control how far the cannonball will go, well, that would mean you could hit any target out to sea. It would be even more useful if we could find a connection between a complex number's angle and distance from the origin and its normal form of a plus bi. So let's try to do that. Since this distance here is a units, while upwards it's b units, that means I really have a right-angled triangle involving lambda, theta, a, and b. So let's go ahead and draw it out separately. The first thing that you should notice here is that we have a right-angled triangle. So we can use the good old Pythagoras theorem, and that will give us that a squared plus b squared is equal to lambda squared. Or in other words, lambda is equal to the square root of a squared plus b squared. Great, so now we figured out the connection between the distance and a and b. But what about the angle theta? Let's try using some trigonometry. Now hopefully you remember that sine is equal to the opposite over the hypotenuse. So that tells us that sine theta is equal to the opposite, which is b, over the hypotenuse, which is lambda. Or in other words, b equals lambda sine theta. Likewise, cosine is equal to the adjacent over the hypotenuse. Now the adjacent is equal to a, and the hypotenuse is equal to lambda. And so we get cosine theta equals a divided by lambda, or in other words, a is equal to lambda cosine theta. But remember, our complex number was in the form a plus bi, and subbing in these two equations into a plus bi gives that a plus bi is equal to lambda cosine theta plus I times lambda sine theta. Or in other words, a plus bi is equal to lambda times, in brackets, cosine theta plus I sine theta. Awesome, we've done it! The connection between our complex number, a plus bi, and its distance from the origin and angle is given by this formula. So what that allows us to do is to figure out what complex number we have given the angle and distance from the origin. So let's try an example, and for that we're going to need a change of paper. Say we want to find the complex number with distance root 2 from the origin and angle 45 degrees. So in our complex plane, it'll look something like this. Now plugging in theta is equal to 45 degrees and lambda is equal to the square root of 2 into our formula gives a plus bi is equal to the square root of 2 times cosine of theta, which is cosine of 45 degrees, plus I times the sine of theta, which is sine of 45 degrees. Now cosine of 45 degrees equals 1 divided by the square root of 2. So we get the square root of 2 times, in brackets, 1 over the square root of 2 plus, now sine 45 degrees is also 1 over root 2, so we get I divided by the square root of 2. And then when you expand this out, you're simply left with 1 plus I. So our complex number is 1 plus I. Cool, that's that, but we can also go the other way around. So say we are given a complex number 1 plus I times the square root of 3. And we want to find out how far away from the origin it is and the angle that it makes with the real axis. Well, remember last time we found everything by considering this triangle and drawing it all up separately. So let's do that again. Here's our triangle, this distance here is the square root of 3, and let's draw it out separately like so. Now we can find lambda using the Pythagoras theorem, which tells us that lambda squared is equal to the square root of 3 squared plus 1 squared, which equals 4. And so lambda is equal to 2. Now to find the angle theta, let's use tan. We know that tan is equal to opposite over adjacent. So that means tan of theta is equal to the opposite, which is the square root of 3, divided by the adjacent, which is of course 1. So tan theta is equal to the square root of 3 over 1, or in other words, theta is equal to the inverse tan of root 3, which is of course 60 degrees. Great, so coming back to our formula, that tells us that 1 plus I times the square root of 3 is equal to 2 times, in brackets, the cosine of 60 degrees plus I times the sine of 60 degrees. Or in the complex plane, we can sketch the following. If you were able to follow through all of that, then props to you. But before we celebrate, we should first go through some of the terminology that we use in math about these things. And for that, we're going to need a change of paper. So first of all, we have a special name for this distance that we call lambda. We call it the modulus of a complex number. And it's called the modulus because in Latin, modulus means measure. And that is precisely what we're doing here, measuring the distance from the origin to the complex number. And we also don't write it as lambda. We use the absolute value symbol. So if I have any complex number z, we denote the modulus of z like this. We also have a special name for this angle theta. We call it the argument of a complex number. Now honestly, I have no idea why we call it the argument. Maybe it's because in an argument you always pick a side, and I guess that's kind of like what we're doing here with this angle, because, you know, we're choosing a side of the plane we're on. Nah, I don't know, it's all waffle. But just remember that this angle is called the argument of a complex number. But we do use the symbol theta, or if we have any complex number z, we can also write it as arg of z. So using proper notation, our formula for any complex number z is going to become z is equal to the modulus of z times, in brackets, cosine theta plus I sine theta. But now it gets quite annoying to have to write the modulus of z times cosine theta plus I sine theta every time, so instead we shorten it by writing the letter r for the modulus, and we make this new trig function called cis theta, which is the same as cosine theta plus I sine theta. In fact, it's called cis because it stands for cosine plus I sine. So now we simply write r cis theta instead of this messy thing. Lastly, whenever we write a complex number in the form r cis theta, we call this form polar form. Because if you think about it, the origin kind of acts like a north or south pole, where you stand up tall, pick out the angle you want to face, and then you go out as far as you want. The other form of a complex number, a plus bi, we call the Cartesian form of a complex number. Sweet, so that's it for this lesson. Next time we'll be looking more at complex numbers in polar form. But beware, the math from now on is really going to kick up a notch. Anyway, laters.